So now we should look at the switching modulator block diagram, okay, circuit diagram. So the only difference is a nonlinear block which was given there is now replaced by the actual diode, which we can assume it to be ideal. Okay, so assuming that, anyways, the input what we are giving v1 of t, as it was written in the previous, the square law modulator also, it's combination of x of t and c of t. X of t is modulating, c of t is the carrier. Okay, and when you give this to the diode basically goes to on condition only during the positive half cycle. As we have assumed the ideal diode, anything which is equal to or greater than 0, you will see at the output of the diode. So anything which is lesser than 0 is all removed. So when c of t is positive, v2 of t is equal to v1 of t. When c of t is negative, v2 of t is 0. So hence we can write v2 of t as m of t by 2 plus ac by 2 into cos of omega ct plus 2 by pi into x of t into cos omega ct plus 2 by pi into ac into cos 2 omega ct. So later on, if you try to basically pass it through a band pass filter, the output of the band pass filter will contain only the carrier signal and the two sideband frequencies, which are fm plus fc and fc minus fm. Okay, so after demodulation we've got the demodulation of AM. Okay, so demodulation or detection is basically the process of recovering the original message signal from the received modulated signal. So this happens at the receiver side. Okay, so what you see at the input of this block is the modulated wave, amplitude modulated wave. Can somebody tell me what kind of modulation is performed there? It is called under modulation. Okay, yeah. So once you receive it, a demodulator will detect the modulating signal there, which is called a demodulated signal. So there are two different types of demodulation. One is square law demodulation, other one is called the envelope detector. So second type is widely used in all practical applications whenever AM modulation is performed. So let us see how it looks like. So this is the circuit diagram of a square law detector, where we at the input side we have got a square law device, or it's nothing but a nonlinear device, and we already know the mathematical model for it. So if the input is v1 of t, which is a modulated wave, v2 will be some scalar a times of v1 of t plus b times of v1 square of t. We limit ourselves to second degree because higher orders will not be contributing too much. Okay, when this is passed through the square law device, what we get is an output which is v2 of t. When you expand it after substituting for v1 of t, which is your AM signal, which was dealt earlier right here, if you can see this equation here, this equation what is written at the end for v2 of t becomes the input to the signal here, which is, after expanding, you get it as equation number 2. So in order to extract the original message signal, we have to pass the signal what we have received here, which is v2 of t, the last equation, equation number 2, through what is called low pass filter, which is shown in the circuit. So I should choose an appropriate RC values so that I get the output as some scalar constant m times of b times of AC square times of x of t, which is your modulating signal. So this is the whole idea behind performing the demodulation. So envelope detector is a much more better practical circuit to demodulate the signal. So we'll see how it works like. So input will be EM of t, or sorry, S of t, which is the modulated wave, and you pass it through a detector diode, so which is nothing but a square law device again, and you have the same RC network. So conceptually both the circuits are one and the same, but the way we are writing is slightly different. So what happens, a standard wave, AM wave, is applied as an input to the detector. In every positive half cycle, the input diode is forward biased. This will basically charge the capacitor C, and when the capacitor charges to the peak value of the input, diode basically stops conducting. Capacitor will have to basically discharge through the resistor R between the positive peaks. Okay, so if you basically observe this wave, what happens is So initially during the positive half cycle, the very first positive half cycle, you can expect the capacitor to charge to the peak value, okay, and later on what happens is, let me use a pen here, okay. So during the discharging process, you keep the resistance, this particular resistance, in such a way that the resistance becomes very large. So this R value what we choose here is a very large resistance value, okay. We purposefully choose this resistance value which will be very large, okay. So based on that, what we observe is, even though the charging process has happened, capacitor is never going to discharge. So when this process is attained properly, so what we get is a kind of signal like this. Let me write it and show it to you. Hold on for a second. Okay. So capacitor will never discharge. Again, the next positive half cycle will appear. Capacitor charges again to the peak value. It goes up. And finally, the negative part will also come. So what we are able to see is the output waveform becoming a sinusoidal signal which is low frequency, which is nothing but your modulating signal. So this is what is going to happen. Okay. So this process basically continues, and the capacitor charging and almost no discharging will happen. So this waveform what is shown here will clearly show the process what is explained then. So diode goes to on condition and discharging will be very, very minimal, and finally the envelope gets detected. Okay, so this is how basically the envelope detector works. So there is a mathematical definition also given to it. So A times of m of t, A plus m of t times of cos omega ct becomes the input to the detector. So we have written the equation for Vs, which is nothing but the modulated signal, and later on I can represent the diode with that equation which is written in the second part, which is this. Okay, right here. Okay, so later on what you will have is 1 by pi into A plus m of t and all other higher order terms which all gets eliminated through the low pass filter. So the same explanation is given even in this case, identical to that of a envelope detector. Okay, so this is what it is. So now if you basically try to see the equation of an AM, so we'll slightly move ahead. S of t is equal to AC cos omega ct plus AC by 2 into cos of omega c plus omega m whole multiplied by t plus AC by 2 into cos of omega c minus omega m whole multiplied by t. So here the carrier component basically remains constant and it does not convey any information at all, correct? If you see the second and third component, omega mt component is there, which is our actual modulating signal. So our interest is only on those components or those terms which contains omega m within it. But the first term, AC cos omega ct, has no omega m at all, isn't it? So what we are trying to do here is, but if you try to see the total average power, the carrier component basically consumes more power compared to the other two components. If you try to find the average power, if you take the first term as it is, so what is the total power consumed by the first one? See here, the total power consumed by this fellow is EC square divided by 2. That becomes the average power. How about this? It will be EC square divided by 4. Correct. And you will also have M there. Anyways, we have missed out this M. So M comes into picture there. So it will be M into EC square by 4. And this will also be M into EC square by 4. So what we observe is the carrier component consumes more power but does not convey any information at all, which is of no use for us. So that is why we always try to suppress the carrier and try to convey only the other two components, which are low and upper sideband components. And when you do that, you say we basically are performing what is called a double sideband suppressed carrier. So power efficiency basically, okay, 100%. So this is what is basically the idea of the DSBSC. So let us talk about the DSBSC modulation now. So DSBSC basically is obtained by multiplying the modulating signal x of t with the carrier signal c of t. So we basically require what is called as a product modulator, which only multiplies the two signals. Okay. So the product modulator output will be what? X of t into cos of omega ct in simple words. So when you expand it, assuming a modulating signal to be a single tone, when you expand it, what you get is basically a double sideband components. Okay, and let's see what are the two different ways of generating the DSBSC wave. First kind is what is called a balanced modulator. Second one is called the ring modulator. Let us see what these are. How does a balanced modulator look? A balanced modulator will contain two AM modulators. It will also contain a 180-degree phase shifter, and it will have a carrier oscillator. So we take the difference of the outputs of two AM modulators. So what will happen? So input is basically x of t. You take a phase inversion, 180-degree phase inversion. What you will get is negative x of t. So the other input given to the AM modulators are the oscillator frequency, which is cos 2 pi fct. Okay, now if you try to see what is happening, s1 of t will have ac into 1 plus m times of x of t cos 2 pi fct. Other one will be ac into 1 minus m times of x of t into cos 2 pi fct. So when you take the subtraction of these two, what you are getting is 2m times of ac times of x of t into cos 2 pi fct. Now for the time being, if you take the example of the single tone case, x of t basically becomes am cos of omega mt. So if you take the am cos omega mt and multiply it with cos 2 pi fct or 2 pi omega ct, what you will get is cos a cos b formula, which is 1 over 2 into cos of a plus b plus cos of a minus b, which means a plus b term is nothing but omega m plus omega c times of t, and next term will be cos of omega c minus omega m into t, which is nothing but your modulating, DSBSC signal. Okay. So what is the ring modulator? What is basically a ring modulator? It operates in two different modes. One is without the modulating signal, other one is with modulating signal. So what happens? Let us also try to see what is the circuit diagram of it. This is what is basically a DSBSC, a ring modulator circuit. So it contains two transformers T1 and T2. One is at the input side, other one is at the output side. And you will use four diodes connected in this fashion. It's in the form of a ring. That is why it is also called as a ring modulator. Now coming to the mode of operation. When C of t is positive, we are in the mode 1 where we do not connect any modulating signal at all. So D1, D2 gets forward biased. You can observe that when input is positive, you basically see, that is when the carrier is positive, you basically see this point to be positive as indicated here and the other one to be negative. So in that case, both D1 and D2 will be conducting and D3, D4 will go to off condition. So because of this, what you see is currents getting generated in these two directions, which are equal in amplitude but opposite in direction. That is why the output basically becomes equal to 0. Why? Because the current induced in the secondary winding of T2 will be opposing to each other, as the primary winding current in T2 are in opposite direction. So what is the conclusion is, whenever there is no modulating signal, the output will always be 0 for a ring modulator, and that should what be the case. Because if there is no modulating signal at all, there should not be carrier, and that is what we are claiming, that the carrier gets suppressed. So when the modulating signal comes into picture, let us see how it works. Okay, so when the modulating signal, which is mode 2, modulating signal is present during the positive half cycle, D1, D2 is anyways in the on condition, and the secondary of T1 is directly applied to the primary of T2, wherein the output is positive. So you'll get the output like this. This is how the output looks like. Whatever is shown in the green indicates the output for the positive. Whatever is shown in the blue is the case for negative. Okay, so this basically shows the operation of a ring modulator. I hope you understood this point, how basically it works. So during the negative half cycle, the other two diodes will come into picture, which again produces the positive voltage but in the other direction, which makes it negative. Okay, so what is the time domain representation of a DSBSC now? So if the input is indicated as AM cos omega mt or 2 pi fmt for a single tone, and if the carrier is AC cos omega ct, the signal what we obtain as DSBSC is product of these two, which is 1 over 2 EM into EC cos of 2 pi FC plus FMT plus cos of 2 pi FC minus FMT. This is what you will get. Okay. How do you write the frequency domain representation of it? Now this is more easier because you've got two cos components there, and the frequency values are FC plus FM and FC minus FM. So what you will have is 4 deltas appearing, which contains FC plus FM plus delta of FC minus minus FM. Similarly, plus delta of FC minus FM plus delta of F minus FC plus FM. So what you get is only two side bands with the carrier suppressed, and the spectrum of that is also shown in the figure. So what you can observe is FC is not there at all. FC plus and FC minus components are readily visible there. Okay, so this is how basically the modulation circuit is going to work. So coming to the DSBSC demodulation, again S of t will become your modulated signal, which is x of t multiplied by cos omega ct. We use again a product modulator, wherein the other input is coming from the local oscillator, which generates the same frequency as that of your transmitter carrier frequency. So what do you get? So when you do that, you will have 1 by 2 AM AC into cos 2 pi FC plus FM plus cos 2 pi FC minus FM into T, which when multiplied with cos 2 pi FCT, what you will get is 1 by 4 AM AC into cos of 2 pi multiplied by 2fc plus fm into t, which is a high frequency component, cos 2 pi fm t into cos 2 pi whole multiplied by fc minus fm into t plus cos 2 pi fm into t. If you observe the third component right here, this becomes your message signal. Okay, so this is how the demodulation is performed, which is obtained after passing the signal through a low pass filter. So what we'll do now is we'll stop at this point, and in our next class we shall move on to the SSP. Okay, thank you.